In this module, our primary objective is to understand how to develop our own function in R. And as you know, in statistical analysis, many times you may not have the available function that you are looking for. Most of the time you may get, but you may not get. And so you have to generate your own function. You have to create your own function, that user defined functions that are very, very useful concept in R. That is the big flexibility the R software has. You can define your own functions here and the compute what you are looking for. And so we'll learn first how to develop user defined function, and what are the different aspects are there that we really need to look into before we generate a new functions, or before we develop a new functions for any specific computations. And then we learn another thing is called the triple dot arguments, the different arguments that we pass, the triple dot arguments, on arguments that can be passed through, and that will help you to pass the arguments of other function within the within any function that you are going to define. And then finally we will learn about the scope in R. What is the static scope, and what is the difference between the scope that R use compared to the static scope. As I mentioned, in this module we are going to learn how to develop our own function in R instead of using inbuilt R function. The R language allows the user to create objects of mode function. These are the true R functions that are stored in a special internal form and may be used in further expression and so on. In the process, the language gains enormously in power, convenience and elegance, and learning to write useful function is one of the main way to make your use of R comfortable and productive. A function is defined by an assignment of the form, say name is the name of the function equals to the function, then argument 1, argument 2, ... expression. The expression is an R expression, usually a grouped expression that use the arguments. Arguments I is calculate a value. Based on this argument I, it calculates some value and return back to you whenever you call this function. The value of the expression is the value returned for the function. As a first example, consider a function to calculate the two samples t-test showing all steps the way we calculate by calculator. Or suppose let's define we define a function 2sem equals to the name of the function is 2sem function. The pass by values are y1 and y2. Then we'll take n1 equals to length of y1, n2 equals to length of y2, yb1 equals to mean of y1, yb2 equals to mean of y2, s1 is variance of y1, s2 is variance of y2, then s is the n1 minus 1 s1 plus n2 minus 1 into s1 divided by n1 plus n2 minus 2, that the standard deviation, common standard deviation. And the TST equals to the test statistic equals to yb1 minus yb2 by square root of s into 1 by n1 plus 1 by n2, and the value that would be returned is TST. You can write TST or return TST. Just in any of the two ways you can return the value. So here I developed a function that will give you the t statistic value. Now we'll apply it. Let's generate a two data set from two normal distribution. One is mean 12 and standard deviation 5, another is mean 24 and standard deviation 5, and then y1 and y2, the two variables, and that can be passed through 2sem, the two arguments that I included there. So y1 and y2 if you pass, then automatically the t stat will give you the t statistic value. The second example, let's define a function that will return the least square estimate beta hat, that is x prime x inverse into x prime y. So the function name that I am defining, say ls. The function x and y, the pass by values are, the arguments are x and y. First argument is the design matrix and second argument is the outcome, the response. See here, I created the return value as the solve t transpose of x into y inverse into transpose of x into y. The way exactly it's written there, the same way I use the matrix notation in this expression, and the return value is the beta. Let's assume the linear model as expectation of y equals to beta naught plus beta 1 x1 plus beta 2 x2. There are two predictors and three parameters. Let's generate a x1 variable from star normal 100 and x2 variable from log normal, total length of 100. Then let's generate y as 2.3 plus 0.5 into x1 plus 0.23 into x2. So the true value of beta naught is 2.3, true value of beta 1 is 0.5 and true value of beta 2 is 0.23. Now let's combine all three variables into a design matrix. C bind 1 x1 and x2. So capital X is the design matrix and y is the response. Now if we pass the design matrix and y as the two arguments of the ls function that I define, then it will give you the estimate of beta, and that is exactly equals to what I have been given as the true value. How to define a new binary operator? If you can recall the matrix multiplication, where the asterisk was given in between 2% symbol. So this is actually one kind of binary variable, that binary operator that already defined in R, but R has the flexibility to define a new binary operators as per your choice. So for that, same way you have to follow. You have to put something in between 2% symbol, and that can be a new binary operator. Now we can define a ls, that least square function, by a binary factor, say percent symbol percent symbol. So we can insert within the percent symbol and create a new binary operator. So instead of calling that ls function, this binary operator might help you to calculate the way you calculate the matrix multiplication. For that, you write the name, write the binary operator at the left side within double quote, then equals to function y x, and then write down the return value, or write your own functions and finally the return value. I just copied the same function that I defined earlier here, and instead of ls name I just replace the ls by within double quote this binary operator created by me. Now this function can be then used as y, this particular binary operator, into x, and that will give you the results. You can try it. Say here, I tried. So y, this particular operator, into x, and that return exactly the same value that generated by the ls function I define. So as I mentioned, matrix multiplication is dollars asterisk dollar. Similarly, the outer product is dollar o dollar, or some existing binary operator defined in R itself. If the named arguments and defaults, if arguments to call functions are given in the name equals to object form, they may be given in any order. That is the one advantage. If you don't give this, just instead of name equals to object, you can directly write object comma object 1 comma object 1 2 comma object 3. So then you have to follow the exact order that you are maintaining. So that is one advantage. Always you write the pass by argument in this format to avoid the ordering of the arguments. Further, the argument sequence may begin in the unnamed positional form and specified named arguments after the positional forms. Positional arguments. Thus, if there is a function, say function 1, fun1 defined by, is this do, suppose the do by is one function that I am using here, the do by sum, this function, variable, graph and group, gr, then the graph equals to true and fun equals to null. Now fun is actually if is not equals to is dot null fun, then match dot fun function fun. If graph is true, if graph, then do the box plot and return the functional value that you are looking for, the do by either mean or whatever you would write. It could be your own defined function too. So here is the example that I am using. Let's generate two variables, say age and gender. Age and gender that has been generated here, and then first we are passing anything for graph. Still we'll return the results with graphs as default is true. As a default is true, so that means even if you don't say anything, automatically the graph would be generated. If you don't want the graph, you can write default equals to false. For example, so do by sum age comma gender comma function equals to mean. Suppose you want to generate the mean, but we are I'm not passing the arguments whether it is true or false, but it will automatically generate the box plot that was defined in the function itself. But if you don't want the box plot, you can just mention graph equals to false. But if you don't give anything about the graph arguments, automatically it will generate the box plot. So as I mentioned, just write graph equals to false and the function equals to median. If I change, say the median would be generated but no graphs. On the other hand, if you write graph equals to true, it will generate the graph. So whether you write true or not true, or omit the arguments, it will always by default generate the graph. The another important part is the triple dot arguments. The triple dot arguments is very useful arguments. This is another frequent requirement is to allow one function to pass one argument settings to another. So that's why it's very, very important. You can use any function within any in a nested structure, and that help you to that the hosting function can be defined such a way that it will allow the arguments of the other functions that are there in the nested structure. For example, many graphics functions use the function pair, that is the graphics parameter function, and the functions like plot allow the use to pass on graphical parameter to control the graphical output. These can be done by including an extra argument, literally the triple dot of the functions. Instead of one argument, you should have to write, you have to write the triple dot of the functions which may be passed on. Say there is another example that I use, say add percent function x multi equals to 100 comma triple dot, and the percent is round x into multiplier comma triple dot, and then paste percent, then percent symbol separate equals to, there is no separation between two arguments of the paste, and then you just say, see, I'm not including anything here about the rounding digits. So the significant digit I have not mentioned in the function anywhere I define. Instead I put a triple dot. So that triple dot can be considered as anything that is appropriate for round functions. So then we can just pass these fractional values, and digit equals to 2 if I say, automatically it will come in a percentage format. Digit equal to 3, then it will be 3 digited. Let's define a do by sum as follows to allow the graphics argument pass through. Say do by sum equals to function variable, then graph as is, as like the earlier definitions, only one arguments that I am including is the triple dot arguments. All are same. Say here the box plot I just included where left side of the formula and right side is the group, comma, and the triple dot, and then return the functional, that the mean or variance, whatever the stratified summary. And now we will see how we can pass the value x lab, y lab, mean, etc. to the box plot. Now see, so do by age, gender, graph equals to true, function equals to median. Now we are passing x lab equals to gender, y lab equals to age, column equals to see red and blue, and change, you can customize the graphs as you want, so that parameter the PAR functions, all the arguments of the PAR functions can be passed through the triple dot arguments. Next we'll see the global variable. The global declaration inside a functions are the variables declared inside a functions are local to the function, called local variables. Note that any ordinary assignment done within the function to the local variable are local and temporary and are lost after exit from the function. The variables declared outside a function are global variables, can be accessed by any functions defined after the global variable declaration. Say x equals to normal 100 and y equals to 3.5 plus 2.6 a into x, and beta is a function that generate the coefficients of that linear model. So the beta function that generates the coefficients of the linear model, then see I am calling beta function without passing anything, it will generate the estimate 3.5 and 2.6 because x and y were defined globally. So any function defined after that can be called directly. If a global and permanent assignments are intended within a function, that provision is also available in R. Then either the super assignment operator this, or the function assigned can be the super assignment operator is this, and the function assign can be used. For example, I am using assign first. Say a equals to old test function, then assign a new environment is dot globe env, then test call, and then another function that I am defining my f function x, then inner f equals to function x globe dot res, that is instead of assign I am using that super assignment operator equal to x square, and then inner f equals to inner f you can pass x plus 1, then if you call my f3 it will give you 16 that has been assigned there. The next we will see how we can define a recursive function. For recursive function, say for example, I'm starting with this example of generating the factorial. So how to calculate factorial? By your own function. So recursive function is function x. Then if x equals to 0, return 1. Else return x into recursive dot factorial x minus 1. So the same function that I am defining, calling the same within the same function. So that is the recursive use of the function, and that will generate the factorial. You can here we have a function which will call itself, and sometimes like recursive dot function x will turn into x into recursive factorial x until x becomes equals to 0. When x becomes 0, we return 1, since the factorial 0 is 1. This is the terminating conditions and is very important. Without this, the recursion will not end and continue infinitely, you should remember. So if I just pass 0 within recursive dot factorial, it would be 1, and if you pass 5, it would be 120. The last one in this in this module is the scope. In R, the free variable binding are resolved by first looking in the environment in which the function was created. This is called lexical scope. And first we define a function called cube, say cube function n, and the square function I'm defining within that is the square n into n, and n into square, where when you're defining the square, we are not at all, as n is already defined, we can easily use there itself. So it looks the environment where n is already defined by the cube functions, so you can call anywhere, even if n is not at all a global variable. The language with static scope looks for a global variable called n, which R first look for a variable called n in environment created when q was evoked. So cube 2 equals to, if we pass 2, then it would be 8. 2 to the power 3 is 8. And lexical scope can also be used to give function mutable state. Follow the code below. Here I just created one code where open.account equals to say function total list and deposit amount. Once deposit, then if the amount is less than equals to 0, then deposit must be positive. Stop and deposit must be positive. And if more than 0, then total equals to total plus amount. Whatever you deposited, it should be added to the total deposit, total available balance in your account before you deposit. And then display the cat amount. So display the amount. Then withdraw, for withdraw functions, for withdraw function amount, if amount is greater than total, you don't have sufficient balance or you don't have that much money, and total is total minus amount, and now display the amount. Then for balance function, cat balance equals to the total that you have. So this is a function that I define, and there if you just see, suppose Rose open an account of 100, Robert open an account of 200, so Rose withdraw 30. Okay, so then the balance is 70, whereas Rose balance, if you want to see, 70, and Robert balance is 200, and Rose deposit say 50, then the balance become 120, and Rose balance is 120, and Rose withdraw 500, it is the error, you don't have that much money. So this is few important aspects while you develop your own functions for your computations. Hope that will help to create your own functions in statistical computation. So we have learned today how to define our own function in R for statistical computation or any kind of computation, and different characteristics that are required to know before you develop the R functions, and what are the different arguments that need to pass through, what is global variable, what is local variable, what is the assignment of the variable in globally and locally, and what would be their implications. And we learn how to define the binary operator, our own binary operators, and then what is the triple dot arguments, how that triple dot arguments can be used through real life data, through some plots, some functions that we developed here. And then finally we got some theoretical knowledge about the scope and the different other aspects of developing a R user defined function.